Imagine trying to hold a conversation with someone who has, like, severe, and I mean absolute, short-term amnesia.
Right. That would be incredibly difficult.
Yeah. Every single word you say to them, they hear it, they process it, but the moment you say the next word, the previous one just vanishes
It's
completely.
completely wiped.
Exactly. They experience every fraction of a second completely independently.
I mean, it would make communication basically impossible. You simply cannot understand a sentence without holding on to the beginning of it by the time you reach the end.
And for a long time, that was the exact problem we faced when trying to get artificial intelligence to understand us.
Yeah, it really was.
Because the basic neural networks, they were brilliant at looking at a single static picture and, identifying a cat, but they were stuck in this isolated present moment. They had absolutely no concept of time passing or of sequences.
Which meant they failed completely at tasks involving speech or language translation or even just predicting what happens next in a time series.
Right.
Solving that required a completely different architecture. It really required giving the machine a memory.
And that is exactly our mission for you today. We are doing a deep dive into a massive, comprehensive Wikipedia article on recurrent neural networks, or RNNs.
It's a fascinating topic.
It really is. So if you've ever wondered how your phone dictates your voice, or how translation apps grasp the context of a whole paragraph, or really just how AI processes the simple passage of time, well, this is the masterclass.
And we're going to cover a lot of ground today.
We are. Okay, let's unpack this. When I was prepping for this, the source kept contrasting RNNs with standard feed-forward neural networks.
Yes, that's the standard comparison.
So as I understand it, a feed-forward network just takes data, pushes it straight through its layers once, and spits out an answer. What makes an RNN fundamentally different?
Well, the crucial difference is right in the name itself, recurrent. It implies a loop.
Okay.
In a standard feed-forward network, the data travels strictly in one direction, from input to output. An RNN alters that fundamental geometry. The output of a neuron at one step is actually fed back into the network as an input for the absolute very next step.
Oh, wow. So it's essentially eating its own output as it moves forward.
Exactly. That loop is what we call a recurrent unit, and it maintains something called a hidden state.
Hidden state.
Right. You can think of this hidden state as the network's internal working memory. So at any given moment, the network isn't just looking at the new piece of data coming in.
It's looking at the past, too.
Yes. It is processing that new data mathematically combined with its hidden state, which contains, well, the echoes of everything it has seen before.
Let me try to visualize this with an analogy. It feels like reading a book.
Okay, I like that.
If I'm a basic feed-forward AI, I read the word "the," process it, and then completely wipe my mental slate.
Right, gone.
Then I read the word "dog," and I have zero recollection that "the" came before it.
It's just a standalone dog.
Exactly. But an RNN carries a running summary in its head. That running summary is the hidden state.
Spot on.
So by the time it reaches the end of the sentence and reads the word "barked," it understands that action in the context of the dog, the mailman, and, everything that preceded it.
That captures the dynamic perfectly. And what's fascinating here is how this architecture looks when you map it out visually.
Oh, yeah, the diagrams in the source material.
Right. If you look at diagrams of RNNs, they often look like these massive, sprawling networks with dozens of horizontal layers. But that visual is actually a clever illusion.
An illusion. Wait, what are we actually looking at then?
You aren't looking at a giant stack of different distinct layers. It is the exact same network, the same layer, just, unfolded in time.
Unfolded, okay.
Yeah. You are seeing a snapshot of the same digital brain at second 1, then second 2, then second 3, laid out side by side on the page.
Oh, I see.
It transforms the input, updates its internal memory, and gets ready for the next step, using the exact same machinery.
It just loops the same hardware over and over. That makes a lot of sense conceptually.
It's very elegant.
But, when I think about the origins of advanced AI, my mind immediately goes to Silicon Valley computer labs in the 2000s or maybe the 90s.
Well, sure. Most people do.
Reading this source, though, the inspiration for this looping computational memory didn't come from computer science at all.
No, it didn't. The origins are much more organic, and they stretch back much further. The very concept of recurrency in this context comes straight from human anatomy and early neuroscience.
Here's where it gets really interesting. We're talking about observations of the human brain from over a century ago.
Right. In 1901, the legendary neuroscientist Santiago Ramon y Cajal was studying the cerebellar cortex of the brain under a microscope.
Just looking at physical brain tissue.
Exactly. And he observed these literal loop-like anatomical structures. He called them recurrent semicircles, and they were formed by different types of biological cells.
Wow.
And then, moving into the 1930s and 40s, researchers began to realize that the brain wasn't just a linear pathway where, a stimulus goes in and a reaction comes out.
Our source brings up Donald Hebb in the 1940s, who proposed reverberating circuits.
Yes, Hebb's work is foundational.
He had this idea that electrical signals in the brain could get caught in a biological loop, bouncing around continuously, and that this physical reverberation might actually be the physical mechanism for short-term memory.
Following that exact thread, in 1943, Warren McCulloch and Walter Pitts published a landmark paper mathematically modeling how neurons work.
Right.
And crucially, they included artificial networks that had cycles or loops in them. They were attempting to use these closed loops to explain medical conditions.
Like
For instance, why a seizure happens in epilepsy, or certain types of chronic pain where a nerve signal simply will not stop firing.
So the idea of an AI memory loop starts with literal brain anatomy. But the source doesn't stop at biology.
No, it takes a pretty sharp turn.
It takes this massive leap into physics, statistical mechanics specifically, which completely threw me for a loop.
You're referring to the Ising model. This dates back to the 1920s, developed by Wilhelm Lenz and Ernst Ising. It was originally a statistical model to understand magnets. Yes. Specifically, how magnetic materials reach physical equilibrium.
Okay, hold on a second. Need a bridge here. How on earth do 1920s magnets connect to an artificial intelligence trying to understand the context of a sentence?
I know it sounds totally unrelated until you look at the math of energy states.
Cool.
In a material, atoms have a magnetic spin, and they constantly influence the spin of their immediate neighbors. They're trying to settle into the lowest possible energy state, which physicists call a local minimum.
Right, they want to be stable.
Exactly. And then in the 1970s and 80s, physicists and computer scientists realized you could use that exact same mathematical framework to model a network of artificial neurons.
So instead of atoms settling into a magnetic state,
You have artificial neurons firing and influencing each other's weights. The network iterates over and over until the whole system mathematically settles into a stable pattern.
wow,
And that stable pattern is what we call a memory.
that is wild. You have neuroscience mapping literal brain loops and physics calculating the energy states of magnetic atoms. And in the 1980s, these completely different disciplines crash into each other to form the foundation of modern recurrent neural networks.
Yeah, by the late 80s and early 90s, with architectures like the Jordan and Elman networks, researchers were using these early RNNs to actually study cognitive psychology.
They were mapping how human beings process sequential tasks.
Exactly.
But as incredible as the theory was, the reality of building these things hit a massive roadblock.
A huge one.
They built the RNNs, they gave them this looping mathematical memory, but the networks had a fatal flaw. They had terrible long-term memory.
Yes, the vanishing gradient problem. This was the great amnesia that almost derailed the entire field of sequential AI.
Let's break this down, because vanishing gradient sounds like, I don't know, a bad sci-fi movie title. To start, what actually is the gradient in this context?
Well, to understand the gradient, you have to look at how the network learns, through a process called backpropagation through time. Let's say the network reads a sequence of 100 words, and then makes a prediction about the next word. If the prediction is wrong, it calculates an error signal.
Makes sense.
It then has to go backward through time, step by step, through the hidden states to figure out which previous neuron made the mistake and adjust its mathematical weight. That error signal traveling backward, that is the gradient.
Oh, I see. It's like tracking down who started a rumor by going backward through a chain of 100 gossiping people, tweaking each person's reliability score as you go.
That captures the sequence perfectly. But
Yeah.
here's the specific mathematical wall they hit. Every time you take a step backward through time to adjust a weight, you use calculus.
Right, the chain rule.
Exactly, which means you are multiplying that error signal by a specific number. And because of how the network's activation functions work, that number is almost always a fraction. It's less than 1.
Oh, and if you multiply a fraction by a fraction by a fraction,
The number shrinks rapidly. If you multiply 0.9 by itself dozens or hundreds of times as you go back through a long sequence, the value vanishes exponentially quickly.
so it just disappears.
Right. By the time the error signal reaches the beginning of the sequence, it's essentially 0. The network mathematically cannot learn from events that happened too many steps ago.
It remembers the end of the sentence, But the beginning is effectively erased from its learning process.
Yes.
Okay, playing devil's advocate here. If it has a memory problem, why not just give it a bigger hard drive? Just throw more modern computing power at it, make the memory banks larger.
Because it's not a storage capacity issue, it's a signal degradation issue.
Oh, okay.
Think back to your gossip analogy, or a game of telephone that stretches for a mile. It doesn't matter how big the brains of the people on the line are. By the time the whisper goes through 1,000 people, the original acoustic message is degraded to noise.
So the underlying architecture itself was destroying the signal.
Big-
So how do you fix a game of telephone where the signal mathematically degrades? Because obviously they figured it out, or we wouldn't be using these systems today.
They solved it with a brilliantly counterintuitive approach. In 1997, researchers Sepp Hochreiter and Jürgen Schmidhuber invented the LSTM.
Right, and that stands for long short-term memory.
Yes.
Long short-term memory, kind of an oxymoron, but okay.
Mm-hmm.
How did this architecture fix the vanishing signal?
By giving the network the explicit ability to intentionally forget.
Wait, the solution to a memory problem was to introduce forgetting.
I know, it sounds crazy, but an LSTM unit contains internal mechanisms called gates, and the most crucial one is the forget gate.
Okay, what does it do?
Instead of blindly cramming every single new piece of data into the hidden state and letting the old, important stuff get diluted by the math, the network actively decides what is useless and mathematically throws it away.
How does it actually throw it away, mathematically speaking?
It uses something called a sigmoid function, which basically acts like a valve. It takes the incoming data and squishes it into a value between 0 and 1.
Okay.
So if the network decides a word like and or the isn't important for the overall context, the forget gate outputs a 0. If you multiply any piece of memory by 0, it is instantly erased.
Boom. Gone.
Exactly. If it's important, it outputs a 1, and the memory is preserved perfectly.
Oh, I see. It's like a central conveyor belt running through a factory.
Right.
Instead of dumping every new piece of trash onto the belt and causing a massive jam, the forget gates act as robotic arms, actively sweeping useless items off the belt. This ensures the core components can travel down the line completely undisturbed.
That is a much more accurate way to visualize it.
Yeah.
By carefully regulating what flows onto the conveyor belt and what gets swept off, the LSTM creates a protected central channel.
A protected channel.
Yes, what they call a constant error carousel. In this channel, the gradient doesn't vanish. The error signal can flow backward through thousands, even millions of time steps without losing its potency.
Wow. And the source also mentions GRUs, gated recurrent units. Where do they fit into the conveyor belt analogy?
Introduced much later, in 2014, a GRU is basically a streamlined, more efficient version of the LSTM.
Like a model upgrade?
Yeah, it combines a couple of the gates to compute faster, but it performs almost identically well on most tasks. But the LSTM, that was the true paradigm shift. It solved the great amnesia.
So they cured the memory problem. They built a network that can remember the past and prioritize the important data. How did researchers actually start putting these building blocks together to do useful things?
Well, this is where it gets really creative.
Because reading through the configurations in the source, the architecture gets wild pretty fast.
It does. Once you have a reliable memory cell like an LSTM, you can start stacking them and arranging them in fascinating ways. One of the most powerful configurations is the bidirectional RNN.
Processing data forwards and backwards at the same time. I remember reading this and thinking, why would you ever read a sentence backward?
Why do you think?
Well, if I say the bank, you don't know if I mean a financial institution or the side of a river until I finish the sentence with was muddy from the rain.
Exactly. A standard RNN, moving strictly from left to right, has to guess what bank means before it sees the word muddy. But a bidirectional RNN uses two separate networks.
Right.
One reads left to right, the other reads right to left.
Hold on, let me push back on that. If the backward reading network has to see the end of the sentence to understand the beginning, how can that possibly work in real time?
It can't.
Because if I'm speaking to a voice assistant, it doesn't know the end of my sentence until I actually say it. Isn't reading backward cheating?
That's a crucial distinction. Bidirectional RNNs are not used for real-time instantaneous prediction. You're absolutely right. They need the whole sequence available beforehand. They are used for offline processing, like translating a document you've already uploaded or analyzing the sentiment of a completely written review. The two networks meet in the middle, combine their hidden states, and the model understands the ambiguous word perfectly within its complete, finalized context.
That makes perfect sense. It only works when the data is already sitting there.
Yeah.
Then there's the encoder-decoder configuration, which the source notes was the secret sauce for early neural machine translation.
Yes, like translating French to English.
Right.
This was a massive leap in the early 2010s. An encoder-decoder uses two separate RNNs. The first one, the encoder, reads the entire French sentence.
Okay.
It processes it step by step until it compresses the meaning of that entire sentence into a single, highly dense mathematical vector. It's essentially a pure language-agnostic concept of the sentence.
It digests the French into a pure thought vector.
Beautifully put.
Huh.
Then it hands that dense concept over to the second RNN, the decoder.
And what does the decoder do?
The decoder takes that concept and starts unfolding it, generating the English sentence word by word based on that pure thought. It doesn't translate word for word, it translates the entire idea.
And we interact with these architectures constantly. The source points out that these LSTM networks powered Google Voice Search and dictation on Android devices for years.
They were the industry standard.
But some of the other applications listed in this Wikipedia article prove it's not just about text.
Not at all. Sequence data is everywhere in the physical world.
Right. For example, they used LSTMs to learn the long-term structure of blues music.
Yes, to compose original blues songs.
Because music, at its core, is just a sequence of notes over time.
Exactly. And it scales up to incredibly high-stakes physical environments as well. The article mentions an RNN system that learned how to tie knots for robotic heart surgery.
Wow. But it makes sense. Tying a knot is entirely sequential. You can't skip step 2 and somehow arrive at step 3.
The precise order of movements is critical. Furthermore, they are being used to predict fusion plasma disruptions in nuclear reactors.
Wait, really? Nuclear reactors?
Yes, a nuclear reactor state is a continuous time series of sensor data. An RNN can analyze that ongoing sequence and predict a highly dangerous disruption before it actually occurs.
That is incredible, and maybe the most futuristic application listed?
Hmm.
Decoding speech directly from the brain of a paralyzed person.
A truly profound application.
They take the sequential firing of neurons in the brain, feed that biological sequence into an RNN, and it outputs the sequence of words the person is trying to say. That is just staggering.
It highlights the raw power of sequential processing. But taking a step back, training a system to do something that complex, without it cascading into a mess of compounding errors, requires some clever engineering tricks during the learning phase.
Which naturally leads us to teacher forcing.
Yes.
When an RNN loops its own output back into itself, what happens if it hallucinates the wrong word at the very start of a sentence? Doesn't it just poison its own memory pool for the rest of the sequence?
That is exactly the danger. If the decoder in a translation task generates the wrong second word, its hidden state is now corrupted by that error.
So the whole thing is ruined.
Basically. Every word it generates after that will likely be wrong, and the learning signal becomes useless because the whole sentence is garbage.
Here's my analogy for this training method. Imagine you're teaching a kid to spell a 10-letter word, like dictionary.
Okay.
If they get the second letter wrong, they write a U instead of an I. If you just let them keep going, the next 8 letters are going to be a confused mess because they are trying to build up a fundamental mistake.
Right, the errors compound exponentially.
So teacher forcing is the teacher stepping in immediately. The kid writes U, the teacher intervenes and says, no, it's an I, now try the third letter based on the correct I.
That's a great way to explain it.
During training, the network uses the actual correct previous word from the training data to predict the next word, rather than relying on its own potentially flawed guesses.
It keeps the training process firmly on the rails. It allows the network to learn the true statistical relationship between the second and third word, rather than getting lost in the weeds of its own early hallucination.
Okay, so we've mapped out this incredible looping brain. We've seen how LSTMs cured its amnesia. We've explored how it translates languages and ties surgical knots.
You've covered a lot.
But if we've solved all these problems, why are we suddenly hearing about a completely different technology? Anyone following AI recently knows that large language models are completely dominating the space, and they aren't using RNNs.
If we connect this to the bigger picture of AI today, the natural language processing field has been overtaken by a different architecture called transformers.
The source is very clear about this shift. Transformers don't use recurrence, they don't loop.
No, they don't.
They use a mechanism called self-attention.
To explain the difference, an RNN processes a sequence one word at a time, updating its hidden state. A transformer's self-attention mechanism works by looking at the entire sequence simultaneously.
All at once.
Yes. It mathematically weights the importance of every single word against every other word in the document all at once.
So it doesn't have to step through it chronologically.
Exactly. And because they don't process sequentially, transformers are much easier to compute in parallel on massive arrays of graphics cards. Plus, they handle incredibly long-range dependencies even better than the conveyor belts of LSTMs.
So serious question for you. If transformers exist, and they are dominating text and language right now with massive parallel processing, why should anyone listening to this care about RNNs? Are they just a stepping stone in computer science history?
Oh, they are far from obsolete.
Right.
Yes. Transformers are incredibly powerful, but that look at everything at once. Self-attention mechanism is extremely computationally expensive. It requires massive amounts of memory and processing power.
Right.
RNNs, by contrast, are highly computationally efficient.
Because they only have to look at one step at a time, carrying that single hidden state forward, rather than holding the entire document in active memory.
Precisely. So if you are running an AI on an edge device, like a smartwatch or a tiny environmental sensor, where you have strictly limited battery and limited memory, an RNN is often much more practical.
That makes sense.
Furthermore, RNNs remain highly relevant for continuous data that is inherently sequential and endless.
Like the nuclear reactor sensors we mentioned.
Yes.
Or stock market data, continuous time series forecasting.
Exactly. A transformer needs a defined window of data, say a 1,000-word context window, to look at all at once.
Right.
An RNN can just sit there processing a continuous, never-ending stream of data, tick by tick, updating its internal state indefinitely without running out of memory. They are fundamentally built for the flow of time.
So they aren't going anywhere. We just have a specialized tool for sequential data.
That's the best way to view it.
Well, this has been an incredible journey through the source material. We started with Santiago Ramon y Cajal, looking at the biological loops in brain tissue in 1901.
A long time ago.
We took a detour through the physics of magnetic atoms settling into low-energy states. We confronted the mathematical wall of the vanishing gradient and saw how the robotic sorting arms of the LSTM, forget gates, saved the day.
That's quite a story.
And we explored how these time-traveling networks paved the way for modern applications, from real-time translation to robotic surgery.
It really is a testament to how many different fields of human inquiry, neuroscience, statistical mechanics, computer science had to seamlessly merge to make this technology work.
It is, and for you listening, I hope the next time you hit the microphone button on your phone and dictate a text message, you take a second to appreciate the mechanics behind it.
Definitely.
Because you are relying on decades of physicists, neuroscientists, and engineers who figured out how to mathematically teach a machine the human concept of time and memory.
And that actually brings up a fascinating final thought to consider.
Oh, yeah.
Think about the fundamental difference we just discussed between an RNN and the newer transformers. An RNN processes information strictly sequentially. It moves from the past into the present, carrying its memories with it, step by step.
Just like human conscious experience. We can only experience the present moment, informed by the past.
Right. It literally experiences time. But a transformer looks at all the data at once. It sits outside the flow of time, looking at the beginning, middle, and end of a sequence simultaneously.
Yeah.
As we continue to build more advanced artificial intelligence, we are shifting from models that process reality, like our biological, time-bound brains, toward models that process information like omnipresent observers.
Oh, wow. That is profound.
It makes you wonder, what does that mean for the kind of intelligence we are actually creating? If it doesn't experience the linear flow of time, is its understanding of reality fundamentally alien to our own?
It's certainly a long way from the amnesiac AI we started with, trapped in a single, isolated moment. Something to chew on the next time you ask a chatbot a question. Thank you for joining us on this deep dive. We'll see you next time.